Hi, welcome to another edition of Calculus 3. Today we are going to continue our conversation about directional derivatives and gradients. Let's go quickly review what we said last time and then continue that conversation. So, directional derivatives and gradients, we said that the topic is an extension of the concept of a slope from Calculus 1 to Calculus 3, where we come across a gradient. So for y equal to f of x, you have a graph of this function and you can only go up or down, and you have a single slope to determine at what rate you go up or down. In higher dimension, for example, when you have z is equal to a function of x and y, you are at some point on a surface and you have a variety of direction to travel. We said you can be ambitious and try to go for the peak at the most fastest rate, or you can go on an incline and be more moderate. So to decide what kind of a slope we are going to have, we need a direction, and that's going to tell us what the directional derivative of the function is going to be and the rate at which we are going to go up or down. So the idea came down to the gradient of function, written as grad f or del f. It's made out of partial derivatives of the function. You can write it in this notation or the other one. And the directional derivative of a function in direction of a vector u is just u dotted with this vector. Okay, so those were the basics, and then we noticed that to be able to carry this thing out, we need to have a review of the derivatives. So that's what we did last time. We started with the concept of the derivative, of the vectors. So we introduced the vectors. We talked about scalar multiplication, regular addition or subtraction. We talked about the norm of a vector. It was just the Pythagorean formula for finding the hypotenuse of a right triangle. The important concept was that we came across the dot product of two vectors. We multiply corresponding elements and add them up, and a major theorem informed us that that quantity is same as the length of a vector times the length of the other vector times the cosine of the angle between the two of them. Important consideration was that when this angle is 90 degrees, cosine will be 0, and as a result the dot product will be 0. So two vectors are perpendicular if their dot product is 0. It's a very important fact to remember. Then we said, well, let's take one of these vectors to be a unit vector, meaning of length 1, and dot it with a given vector. As we go around, we get different values for this dot product. As the direction of the unit vector changes, the dot product is going to change. So the maximum value of this product is going to be when the unit vector lines up with our given vector, in which case we are going to have the highest value. And if the unit vector is in opposite direction of the given vector, we are going to have the lowest value. These two facts are going to be important for us today, and we are going to make use of that. Of course, in this green direction we are perpendicular to the direction of A, and as a result the dot product is going to be 0. So we described where the gradient comes from. It's a package essentially that contains our partial derivatives, and the directional derivative was introduced last time. We took an example. For example, this function, it's a elliptical paraboloid. We calculated the directional derivative of it at a given point in a certain direction. So I want to make sure you review that before we continue on the journey today. So today what we are going to do, we have a list of applications of gradient of f. This is some of the applications, believe it or not. The application is much longer than this. So But the ideas are all very intuitive and also very important. So let me first try to explain what these things mean, and then we go back and apply them to some specific problems so that you see how to solve related problems. So applications of gradient of f. Gradient of f for a function of two variables is a vector of two variables of two components, fx and fy. Function of three variables is going to be of three components, partial derivative of your function with respect to x, y, and z, and so on if you had more variables. Important observation number one: if you want to travel in a direction where your function increases at the fastest rate, then travel in direction of the gradient of the function. This is crucial in all the observations that we are going to do in item 2 and some of the observation later on here in item 6. Let me go ahead and explain this thing in a picture first, and then we come back. So let's go to a very intuitive idea. Okay, this is a weather map. So we are living here in Southeast Texas, quite hot here, and every now and then you like to go someplace that is cooler. So you can ask the question, where can I go within a radius of 100 miles that's going to be 10 degrees cooler than here? So for a certain distance you travel, you want to hit the coolest spot. This is a standard question in engineering or mathematics. If we are at a certain value of the function, in which direction should we travel so that that function increases at the maximum rate or decreases at the maximum rate? So for example, if we are in the northern territory, say in the Rapid City or somewhere, you probably want to go somewhere that is warmer. And of course, if you go all the way to Mexico, it's of course warm. So the issue is, for a unit distance that you travel, which direction you go so that you get the warmest? Or if you are in southern regions, which direction should you go so that for per mile that you travel, the temperature drops by the maximum amount? Okay, let's go turn this problem in a mathematical fashion. Suppose I have a metal plate here, and the center of this thing is hot and out here is cool, and this is essentially the weather map of that metal plate. In engineering, you are going to call these things isotherms. Isotherms are the curves along which the temperature is a constant value. So on this red curve, the temperature is some value, on the green one is the higher one, and the blue one is the higher one, and so on, and presumably in the center of this plate is the hottest one. Now suppose I am at some point on this periphery over here. Question I ask, which direction should I go so that I get hottest for same amount of distance I've traveled? Well, you might say, well, come all the way to the center, that's the hottest. But the question is, in the vicinity of our neighborhood. We are not going to be traveling from south of the United States to the north of Alaska in a single trip. We are just making a mile at a time. A mile at a time, where should I go so that it becomes hotter? So, and then perhaps we finally come to the green line, and then finally come to the blue one, and eventually we reach the hottest place. Well, so here the question is, which direction should I travel so that the function is going to change by the fastest rate? And suppose we have a heat-seeking device, like a particle that's going to travel on this trajectory, chasing the hottest next spot. In which path would it travel? Well, we are going to solve that problem and show you that in this particular case, The way you are going to be traveling here is that you're going to travel perpendicular to the first isotherm, and then perpendicular to the next isotherm and next one, and so on. Actually, if you draw all the isotherms, you're going perpendicular to all of them until you reach your maximum temperature. So this is one problem we are going to solve. And of course, if you want to go toward the cooler territories, you'll go in the opposite direction of that. So that is one topic we have in mind. So direction of maximum increase, you simply take the gradient of your function, and that's the direction at which you have to travel for the things to change at the maximum rate. Now, why so? We explained this thing last time when we talked about if I'm doing the dot product of a variable vector u with respect to a, I get a quantity. That quantity is going to be highest if I line up with a, and it's going to be lowest if I'm going in the opposite direction. What does that have to do with our problem? The connection is in the directional derivative. We said directional derivative in the direction of u is the u dotted with our gradient. So if you want this to be the highest value, pick u to be in direction of gradient of f. If you want this to be the lowest value, then pick u to be the opposite of this, that is negative of that. If you don't want to change at all, then take u to be perpendicular to this, and therefore your dot product is going to be 0. So this simple observation that we had here with respect to the vectors explained quite a bit for us. So the reason for the statement that we are making, direction of maximum increase, is exactly the gradient of the function. And at what rate are you actually going to go up? As we showed before, its maximum rate is going to be absolute value of the gradient. If you go in the opposite direction, well, you're going to have the maximum decrease and such. Tied to this topic, direction of normal to the level curve or level surface of some function. That direction of normal is exactly the gradient of the function. Now, if you want to write the equation of a normal line, we have used tools we have learned in Calculus 2 perhaps, or perhaps even Calculus 1. We have a standard way of arriving at that. Same way, if you want to find the equation of tangent line to a level curve, well, we are going to take this r minus r0. If you dot it with gradient of f equal to 0, that's going to be the equation of tangent line. Same way, in higher dimension, tangent plane, that's r minus r0 dotted with gradient of the function equal to 0. That's going to be the tangent plane to a level surface. And that topic I just showed you, if a heat-seeking particle is traveling, seeking out the next hotter place, in which direction is going to travel? It's going to travel so that the derivative of its position with respect to time is going to be parallel to the gradient of f. Okay, so let's go ahead and take the some examples, and then look at this to see how the problem goes. So suppose I have let's go to this problem with a simple picture we had to show. Let's see which one it is. Suppose a metal plate is heated like this. So we are on a flat metal plate. It is heated so that the center of it is hot and around it is cool. Now, if we want to graph this thing in 3 dimension, the graph's going to look something like this. Okay, so this is the graph of the same function. Remember, we are on a flat plane, flat sheet of metal. The temperature at different places is a different number. So we are plotting the temperature on vertical versus x, y, which is where our metal plate is sitting at. So metal plate is sitting down here. The center of that plate is hot, and as you go toward the edge of it, it's cooled down. It's going to cool down. It has these isotherms or level surfaces we talked about before. And then the question is, if we are wanting to go from one location to the next location, in which direction should we travel so that we actually gain the highest amount of temperature per unit of distance we have traveled. Let's take a look at that problem. Okay, let's go back here. So we have a rather simple function here. So we have So we are going to take examples of these topics and see how we are going to attack it. So suppose I have z is equal to say that 2 minus 4x squared minus y squared. So what is this? This is a temperature on a metal plate. What does this look like? We drew the picture for it. We said, for example, out here is kind of cooler, and then as we come toward the center it becomes hotter, but not in a circular fashion, which would have made our problem a lot easier. One side is heated differently than the other side. So question is, suppose I am at a location on this plate, some location here, say it is say 2 and 3. Okay, now the question, where would I go? In which direction should I travel so that temperature is going to increase the fastest? If we are at point 23, in which direction should we travel? Should we move so that temperature increases at the maximum rate? And what is that rate? Okay, if you want to call this thing z is equal to f of x and y, or you could also leave it just as z. First of all, we go ahead and calculate gradient of this function. Gradient for a function of two variables is very easy. It's partial with respect to x and y. So gradient of this function will be partial with respect to x, it's just minus 8x. Partial with respect to y, minus 2y. Okay. If you are at the location x and y, go in direction of this vector so that your temperature is going to grow at the highest rate. So suppose I am at 2, 3. So if x is 2, y is 3. So if I'm at this location, then my gradient becomes, so x is equal to 2 becomes minus 16 and then minus 6. Is that right? So gradient is gonna be, this is gonna be a very long vector. You might as well divide it by something. This is telling you go in a certain direction. Of course, you don't need to go all the way. So this vector that we have here is going all the way here. This gradient of f looks like this, but you just go small direction, small distance. Why why stop here? Because as soon as you move, everything changes. X and Y changes. You have to recalculate everything, and then you're going to get a different number. So as soon as you move, this is going to change, and then you're going to get a different number and so on. So at the end, you end up going on a curve as opposed to traveling alongside all of this all the time. But if you are right here, in which direction should you start moving? That's the direction to move at. We are not saying you're permanently going to go in that direction. Problems a lot more complicated than that. At what rate are you going to gain temperature? The rate at which you gain the temperature, that is this maximum slope you can sense, is the gradient. If the absolute value of this, that is, you just take the square root, take the quantities and square them, take square root of that, and that's the rate, the maximum rate you can hope for. So here in this case we get, what is that, 256 and then another 36, and we get the total of 200 and what's that, 292, whatever that is. So the maximum slope you can have while you're going up this peculiar mountain is square root of 292. What if you wanted to go to cooler region? Well, you would go in the opposite direction of this. So same question, let's write it in different which direction should you go for getting decrease at maximum rate? But the answer is minus gradient of f. That's the minus of this vector, so it's going to be 16 and 6. So that's going to tell you go in this direction for the cooler region, and then you will be going in this direction for the hotter region. Okay. Well, while we are here, we might as well jump to problem number 6. What is this curve at which we have to travel so that at every moment we have highest gain in temperature as we are going to go down? So we are traveling along some vector. Let's consider that vector r. So let's call this thing we are traveling on this. Let's consider r as a function of t. That's a location that we are after. How should we go? Well, r prime is going to be our velocity, and if we want to go in the direction of gaining the highest temperature, that r prime has to be proportional to gradient of f. So if the problem was posed like this, a heat-seeking particle travels in direction of maximum heat increase. Find its trajectory if it, say, starts at, let's take the same starting place, if it starts at 2, 3. Okay, so this heat-seeking device is going to line itself up with gradient of f so that it chases heat at the maximum rate. So r prime, so let's consider r to be position. So r prime is going to be the velocity. That particle is going to adjust its velocity so that it will go in the direction of gradient of f. So r prime is going to be a multiple of, so whatever multiple we don't know, some multiple of gradient of f. So what does this mean? What is r prime? R prime is dx dt and dy dt. R itself is the position x and y of the particle. So this is going to line itself up with the with gradient. Well, what does that mean? The first one is equal to the first, second is equal to the second. So we are going to have dx dt is going to be some multiple of f of x, and dy dt is same multiple of f of y. Well, one way to simplify this, hoping for an answer, is taking the derivative of y with respect to x. That's the easy way to get rid of the y's, and then we are going to get fy over fx. Well, that's going to be a differential equation. Differential equation is a course that you're going to take next. Full story is going to be explained to you there, but some simple cases of differential equations are going to be in this book as well. Actually, you can find out. Here is a very simple case. Fy, we had fy was minus 2y, and fx was minus 8x. Is that right? Fx was minus 8x. Okay, we simplify this thing, becomes dy dx is equal to y over 4x. Okay, this is going to be the simplest differential equation you are going to see later on, and you can actually solve it here. It's called separable. Separable for the reason that you are going to see momentarily. If I write this thing as dy over y is equal to dx over 4x, you notice that the y's got separated from x's. That's why it's called a separable differential equation. Okay, what do I do now? Well, easy. You take an integral of both sides. Let's assume y and x are positive, so I get a little bit of a reprieve here. So antiderivative of dy over y is logarithm of y, same way here, and then we need a constant, or you can write constant on both sides. Okay, now I exponentiate both sides, so I'll have exponential of logarithm of y is exponential of 1/4 of logarithm of x plus c. Exponential of logarithm of y, you remember that's just y. This one, let's go ahead, break it up into several pieces. First, I write this exponential of logarithm of, take the 1/4 inside, and times the exponential of c. You remember, if you have b to power of m plus n from pre-calculus, you can write it b to power of m times b to power of n. So exponential can be broken up in this style. So y becomes x to power of 1/4, and exponential of c, let's write exponential of c. To make this thing look simpler, I just give it a name, call it k, or let's hold on for a moment to clean up my equation. I take both sides and raise it to the power of 4, so it becomes y to power of 4 is equal to x times exponential of 4c. So my equation looks like this, and you can write it in a variety of fashions. For example, if you want to write it in terms of x, you can write x is equal to y to power of 4 over exponential of 4c. You can write the equation in a number of ways. Now what is the c? Well, you adjust this thing to your starting value. Starting value is starting location at which we start the journey. So our starting value was 2 and 3. X was 2. So our starting value is x is equal to 2, y is equal to 3. So if x is equal to 2, we have 2 is equal to y is 3 raised to power of 4 over exponential of 4c. This tells me exponential of 4c has to be 2 over 3 to power of 4, or in other words 2 over 81. So final answer, x is equal to y to power of 4 divided by, and this is 2 over 81. So I can simplify this thing and say x is equal to 81 over 2 times y to power of 4. So what does all of this mean? It means the particle that starts here is going to travel on this curve, and that curve has this equation that x is y to power of 4. That is what I showed you on this picture. Let's go ahead and look at this thing one more time. Okay, this blue curve is an example of the trajectory of a heat-seeking particle. It's going to travel on this. Okay, let's go ahead and take a look at another example, another problem that we are dealing with. So what we did is that we figured out the direction of maximum increase and direction of maximum decrease is going to be opposite of that. Path of a heat-seeking particle, simple problems we can find this, but full story requires a next class. Now let's go ahead and explain normal to a level curve in tangential line, in tangential plane, and so on. Let me go ahead and pick a problem with a little bit of more flavor to it, not as simple as the one we looked at with that parabolic equation that we had. This z is equal to 2 minus 4x squared minus y squared. That's a very simple looking formula. Let's go after something a bit more involved. Okay, suppose we have considered the curve. Let's see, y cubed plus 5xy is equal to 7 minus x to power of 4. Okay, that's not anything that any of us has seen before. Just pull it out of my head, and it's a peculiar looking function. Okay, this type of thing do show up all over the place. We want to learn how to find the tangential and normal lines and vectors and such things. So find, here's a list of things we want to find. Perhaps a normal vector, or the normal line, or perhaps the tangential line, the tangent line, to its curve at, now let's pick a point. So I just made this so that we have an easy point on it, point 1, 1. Okay, now this is a problem you have done in Calculus 1. You should have done this problem in Calculus 1, and we have talked about this thing before, but let's go ahead and look at it from the point of view of gradient and see how we use the gradient to give clean-cut answers to this thing. Now again, before we dive into all the formulas and such, what are we talking about? Let's go back to here and let me go to the next demo. Okay, here is that thing, y cubed plus 5xy is equal to 7 minus x4. Here's the graph of this. I bet nobody has seen some peculiar looking curve like this. So it's just some graph. If you write an equation between x and y, well, typically the graph of it is some curve, and that's what we are looking at. Okay, once you have such a curve, you can wonder about, if I want to build perpendicular to this, in which direction do I go? If you want to make tangent to this, in which direction do I go? So normal, by normal I have drawn this thing. This is a normal. I can track it for you so that you see. Okay, here it turns quickly, so you notice normal is perpendicular to your curve. So we are going all around. The question is, what is this vector? How do I find that vector? We just explained why you want to find that vector. If you want to go in direction of something increasing at the fastest rate, that's the way you want to go. Okay, now what about the lines we talked about? Well, let's go ahead and draw some of these things. Normal line is just that vector you extended all over the place. That's the normal line. Tangential line, what do you mean tangential line? Well, I'm supposed to be right here. That's the tangential line, that green thing. We want to find that. And again, as you go around, well, my hand's supposed to stay steady on the curve, but I kind of have a hard time with it. That's what we are after. So normal and tangential are the two most basic things we expect ourselves to be able to calculate. And the question is, well, how do you use gradient to get these things? And the answer is very easy. Again, we are just repacking what we have seen in Calculus 1 and writing it in a nice style. So what do we do? First of all, we take this thing, convert it to a function of two variables. You have many ways of doing that. Easiest one is just bring everything to one side. So take z to be y cubed plus xy. Okay, so bring everything to one side. So it becomes plus x4 minus 7. So z equal to 0 is the curve. The level curve of this, when z is equal to 0, is exactly the curve that you want to look at. Next, question is, I want that normal vector. Let me go back here before we lose track of this thing. Let me erase this thing. Okay, we want this vector. How do I easily get that vector? And we are given a specific point 1 1. I'm a little bit off from that, so those of you who play a lot of video games should be a lot better than this than I am. So very easy. Normal vector is in direction of gradient of this, gradient of z, or if you want to call this f of x and y, will be gradient of f. So what is gradient of z? Gradient of z, let's just use z, that's cleaner. Zx and zy. So two derivatives. So zx, carefully differentiate with respect to x. What do we get? So derivative of y with respect to x0, derivative of this with respect to x. What is that? Come along with me, tell me what's the derivative of this. If you said 5y, you are the grand prize winner. Plus, excuse me. we are not finished. Derivative with respect to x is a 4x cubed, comma. Now same thing with respect to y. Derivative with respect to y is 3y squared. Derivative of that with respect to y is 3y squared. Derivative of this one with respect to x is 5x. Okay, now we said at a certain location, like for example 1 1. At 1 1, gradient is, well, I chose easy numbers. 5 and 4 is 9, and 3 and 5 is 8. Okay, so vector 9 8 is a normal vector. So that peculiar looking like a broken finger or something. Let me just erase this thing and go back to the okay, we are at this point. The question is, which way do I go so that I'm perpendicular? Well, the two components were what? 9 and 8. You go 9 in this direction, 8 in that direction. That is your normal vector, or any multiple of that is a normal vector. Okay, now next question, what is the equation of normal line? We are going to have a lot of questions like this later on. We might as well get used to this. Now, normal equation of normal line. Well, if you have a vector, horizontal component is 9, vertical component is 8. What is the slope of it? Slope of it is, of course, 8 over 9. So you are at the starting point 1 1. You are going at the slope 8 over 9. What would be equation of your line? Back in college algebra, y minus y of a given point is equal to slope times x minus x of the given point. This is the equation of the normal line. If you want to write it in general, so y minus the y of a given point is equal to, now in the numerator you have partial with respect to y of that function at the point of interest. In denominator you have partial with respect to x of same location. Okay, you have to calculate them at the location and get the numbers, and then x minus x0, that's going to be general equation of normal line, general equation of normal line. And if you want to multiply it and make it look nicer, be my guest. Another type of a question they ask you in college algebra, calculus, and so on, equation of tangent line. Tangent line, of course, if this is your normal vector, the tangential one, which is perpendicular to normal, tangential one is going to have a slope that is the negative reciprocal of this thing, that is m, let's call it m prime, is equal to minus 9/8. Is that right? So if this is m, let's write it in the right color. So if this is m is 8 over 9, for the perpendicular, the slope is negative reciprocal. So how would you write the equation of tangent lines? So y minus of y of a given point is equal to minus 9/8 times x minus x of a given point. Okay, if you wish, this has a nice look to it. If we cross multiply it, let's do cross multiplication. 8 times y minus 1 plus 9 times x minus 1 equal to 0. And what is 8? 8 was partial derivative in y direction. Let me write this thing in front so it causes less confusion. X minus 1. And what is 9? 9 was partial derivative in the x direction. So here is general equation of tangent line. General equation of tangent line, let's write it nicely. X minus x of a given point times the partial derivative with respect to x at the point of interest plus y minus y0 times partial derivative with respect to y, again at the same point. This is the equation of tangent line. Now, if we were in a higher dimension, then there will be, instead of a curve, there will be a surface, and that surface is going to have a tangent plane. Your function is going to have x, y, and z's in them, and the format is the same. So let's write it here. General equation of tangent plane goes as x minus x0. I'm not, well, maybe I should. x0, y0, z0. We're going to write a lot of these things. Y minus y0 times f with respect to y of x0, y0, z0. And then finally z minus z0 f with respect to z of, same thing. So equation of tangent plane is very clean. Now, as a finale for this thing, how do we write this thing using the notation of gradient? Well, x, y, z is arbitrary position. Let's call it r. x0, y0, z0, that is the given point. R minus r0 is a vector that has these three components. If we take this and dot it with gradient, you remember gradient has several components, and when we do dot, first component multiplies the first component, second component, and so on. So if we do this and calculate this gradient as that point of interest, and that point of interest, let's clean it up and write it as r0. So r0 giving our position. If it is x and y, it's x and y, and 0 and z, all the same. So equation of, here's a very clean looking equation for tangent line or tangent plane. So equation of tangent, now if you want to be in 2 dimension, it's going to be tangent line. 3 dimension, tangent plane. Higher dimension, oh, it's called hyperplane. It's same story, but the equation itself becomes super clean, and but you need to understand what does it mean. So is it gradient, partial derivatives, and this is the displacement from the position. Okay, on one hand very intuitive idea, on the other hand the notation is becoming harder, but well, we are in calculus 3, we don't expect easy stuff here. So you are going to have a bunch of exercises here, and hopefully you will be enjoying them, and they'll be relatively simple, even though what we are, our notation is somewhat complicated. Okay, until next lecture, good luck and God bless.